All right, now it's time to move to lecture 2, and we are going to talk about heat. So we are starting to talk a little bit about energy. Heat is actually an important concept that we are going to introduce now, and we are going to introduce it by talking about its definition, and then we'll spend quite a bit of time about heat capacity. We are already going to see the relationship between heat, temperature, volume, pressure, all those variables that we have discussed about in the first lecture already. Okay, so the two equations that are on this first slide, of course, are just to whet your appetite, and I'm going to describe this in a few minutes. Of course, things that we know about heat is that the everyday definition of heat is not quite accurate, so we are going to try to make sure everybody's on the same page with heat. Um, so there is what heat is and what it is not. So, of course, heat is related to energy. I think that we are all good with this. Heat is related to temperature. I think that's not a problem either. Now, here is the thing that people sometimes forget or do not appreciate is that heat is related to transfer. We never talk about the heat included in something. That's not a concept that we use in physics. In physics, heat is always an energy that's transferred between two bodies. Okay, that will be the heat. The heat will always be looked at as transfer of energy. We do not talk about the amount of heat included in an object. Okay, so that means that the definition we are going to use is that heat is thermal energy in transit. Okay, so you see that sentence that I underlined, really uh, signifies, uh, includes, sorry, all the three concepts. Heat is an energy, heat is related to temperature, so it's thermal energy, and it is a transfer, so it's in transit. So heat is thermal energy in transit. Of course, it's measured in joule because it's an energy. Um, and of course, the rate of heating, so which is of course joule per second, measured in watts, just like the usual power units that we use in physics. Okay, so again, using empirical information, experiment indicates that heat spontaneously transfers from hot to cold body. So of course, this is a central concept that we are going to discuss a lot. But heat transfers from hot to cold body. It turns out that you can also transfer heat the other way. Okay, but one law of thermodynamics is that if you want to transfer heat from a cold body to a hot body, something else has to take place. So the good example that we typically use is the fridge. A fridge clearly violates the idea that heat transfers from a hot to a cold body. In a fridge, heat goes from a cold body to the hot body. But of course, there is another process that takes place. You have a compressor. You have methods to actually make this happen. So heat spontaneously, so the word spontaneously, of course, is important, spontaneously transfer from hot to cold body, and it can transfer the other way around if there is another process taking place. So of course, a transit uh, is a key attribute. And as I said before, an object by itself does not possess a quantity of heat. It does possess a quantity of energy, but not of heat. Now, there is a concept that's extremely important and is going to come very often in this course. So it's the one of heat capacity. And there is an asterisk there, and it's actually described in the book. And of course, it is an important concept to discuss. I just told you that heat is not a property that it's not something that the body can have. It's transferred. So of course, when you talk about heat capacity and saying it's the energy inside of a body, that it of course it means okay, that makes no sense because I just told you that heat is not the energy inside. But anyways, heat capacity is a concept by itself that's actually fairly simple concept. is essentially the amount of energy that you need to supply to an object to raise its temperature by a small amount, dT. Okay, of course, the heat capacity goes the other way around too, is that how much energy, how much heat is transferred from a body that that's temperature goes down by 1 degree. Okay, that's the usual idea. And of course, how much heat is called the heat capacity. And of course, this is written as delta Q is equal C dt. Basically, C is this constant of proportionality between the amount of heat that's transferred and the temperature. Okay, so the way you can think about this is that the heat capacity is really a definition of the relationship between heat and temperature. Okay, and again, um, delta T dt is really the temperature difference, and delta Q is the heat that's transferred. So you see that if there is no temperature difference, there is no heat um, that's transferred between bodies. Okay, so the definition is an important one. The heat capacity is the derivative of the heat with function of temperature. So another way, the best way to remember this is that the heat capacity is the amount of energy that you have to transfer as heat to raise by the body by 1 degree. So it's a heat per degree, if you will. So that's how you say dq over dt, and the amounts are tiny. So we can use an example. We have, and the examples are going to be like this. Oh, sorry. I apologize about this. Uh, the example are going to be like this. Suppose that you have 125 grams of water, and then you know that the heat capacity is 523 joule per Kelvin. Okay, so what the heat capacity of water is, of course, the heat capacity uh, uh, joule per Kelvin. So you need to divide, you need to know the heat capacity for a unit mass. So you need to divide by the mass, and you get 4.18 times 10 to the power 3 joule per Kelvin per kilogram, because it's the amount of heat per kilogram. You can also do it per volume, and in that case, you divide by the volume of the amount of water you have, like 125, okay, gram. And then, of course, you also have the molar heat capacity, which is the heat capacity. So it's the amount of heat that you need to raise a mole of that material by 1 degree. So basically, you end up with the specific heat capacity, which is the heat capacity per unit mass, and the molar heat capacity, which is the heat capacity per mole. Note that the heat capacity per unit of mass, so the specific heat, is usually written with a lowercase c, just like written here. So as a good exercise is you could calculate the molar heat capacity of water. Of course, doing the conversion between grams and mole is fairly straightforward, since you know that 1 mole of water is 18 grams, as we discussed in lecture 1. Now, the problem is, this is all very nice, but you should be concerned about this definition of heat capacity, which is the amount of heat that you need to bring to a body to raise the temperature by 1 degree. Because you know that it's going to depend how you do it. There are many different ways to do it. For example, you know, if you cook and you put the cover on the pan, you know that it's going to be constant volume. If you leave it open, it's going to be constant pressure. So clearly, the amount of heat that you have to bring to bring the water to a boil is going to be different in each case, right? So this is the question: how can you heat a gas? This is a big question. How can you heat the gas? So different ways to do it, of course. Okay. So the question is, it is going to depend on how we do it, and there's nothing we can do about this. We just have to be able to uh, to explain and to provide a description of the constraints. And this is something that we see very often in thermodynamics, is that we have different conditions under which we work. And these are called the constraints. So we can work, for example, at constant volume. So this is a typical example of what it is. It's just a container that you heat at constant volume. Or you can also work at constant pressure. So constant pressure, you have the piston there that we can actually move up and down. If you were actually keeping the vessel open, it would be constant pressure. That would be the atmospheric pressure. So remember the description I had in the previous slide about heat capacity as derivative. It turns out that the derivative are actually partial derivative because heat Q depends on a number of other variables, as we just discussed, volume and pressure, for example. So we are going to talk about uh, partial derivative, and we have to give the constraint. So this is something that we do in calculus, in differential equations, differential equations, yes, is that we tell which constraint we have. So when we put a lower script v, that means that we had constant volume. When we put a lower script p, we have a constant pressure. And we expect that the amount of heat that we have to bring at constant volume, or the amount of heat we need to bring at constant pressure to raise a gas, for example, by 1 degree, they're going to be different. So CV and CPs are two values, heat capacity at constant volume and heat capacity at constant pressure, that are going to differ. And in fact, so this is what I just said, we have the constraints here. In fact, we know that CP is going to be larger than CV. The amount of energy that you have to bring at constant pressure is larger than the amount of heat that you have to bring at constant volume for increasing the temperature by the same amount. The best way to remember this is why you cover the pans when you try to boil water for spaghetti, for example. Okay? Why is that so? Why do you need more heat to increase the temperature at constant pressure? Well, the reason is that when you have constant pressure, some of the energy that you provide as a function of heat is actually used to increase the volume. So there is actually work done. So there is some energy that doesn't go into increasing the temperature, but instead it goes into increasing the volume. On the other hand, at constant volume, there is no work to be done because unless you, of course, it starts to boil over and and the cover on your pan is actually start to explode, which is not exactly what we are doing here. But if at constant volume, um, we do not have work done, therefore we don't waste, if you will, energy. All the energy that you provide as a function of heat, as a form of heat, is actually used to increase the temperature by 1 Kelvin. So that's nice. So this concludes lecture 2. Just to summarize, we introduce heat. What's important for heat is that it's a thermal energy in transit. This is one of those definitions that you should just keep in mind for the rest of your life as a physicist. And the heat capacity, of course, has been introduced. I discussed that. One thing that we already discussed here, and this is really a take-home message of this lecture, is that in thermodynamics, the variations of some functions like temperature, heat, whatever, all the functions that we are going to consider, they are going to be those variations are going to be different as a function of the constraint that we impose the system. And the constraints are usually related to constant pressure, constant volume. We also see constant temperature, constant entropy. But all those concepts can be translated into mathematics very easily using the language of calculus. So that's what we are going to do. And let's make sure that you review all those concepts, and we'll be ready for lecture 3.